Welcome to Mr. Chalk's Revision Tips. In this video, we will look at the Haber process, conditions for the Haber process, and what we mean by equilibrium. So the Haber process combines nitrogen from the air with hydrogen derived mainly from natural gas, right? And it makes ammonia. The reaction is reversible and the production of ammonia is exothermic. So to increase the rate of reaction, an ion catalyst is used. So if you look at the equation underneath, if we think about what the double arrow means, it means that the reaction is reversible. When a chemical reaction happens, energy is transferred to or from its surroundings. When energy is transferred to the surroundings, this is called an exothermic reaction and the temperature of the surroundings increases. However, when a chemical reaction happens and energy is transferred to or from the surroundings, when the energy is transferred to the mixture, it then goes and decreases in temperature, and that would be an endothermic reaction. The temperature of a system at equilibrium can be increased or decreased. So the relative amount of the products at equilibrium increases for an endothermic reaction if the temperature is increased. So the relative amount of products at equilibrium decreases for an exothermic reaction. So if the temperature of a system at equilibrium is decreased, however, the relative amount of products at equilibrium decreases for the endothermic reaction. So the relative amount of products at equilibrium increases for an exothermic reaction. So at a temperature of 450 degrees, that's the temperature that we use for this process. So the reaction of nitrogen and hydrogen is reversible. The forward reaction is exothermic. So if we look at explain why the temperature of 450 degrees is an optimum temperature for the Haber process, you've got to be thinking of something like, because a high temperature would reduce the equilibrium yield. A high temperature would favour the backwards reaction because a lower temperature would reduce the rate. And if we're explaining in terms of particles why increasing the temperature makes the reaction go faster, it's just because the particles have more energy, so move faster, have more kinetic energy, so there will be more successful collisions. When the concentration of all the reactants are increased, more molecules or ions interact to form new compounds, and then the rate of reaction increases. When the concentration of a reaction decreases, there are fewer of the molecules or ions present, so therefore the rate is also decreased. So if we think about why does the yield of ammonium at equilibrium increase as the pressure is increased, basically as you increase in pressure, that almost artificially increases the concentration. So you get more moles or molecules in the same volume. So at equilibrium, or the reaction moves in the direction which reduces the pressure or volume, which means that you'll go and make more complex molecules from the smaller ones. If the concentration of one of the reactants or products is changed, the system will no longer be at equilibrium and the concentration of all the substances will change until equilibrium is reached again. If the concentration of a reactant is increased, more products will be formed until equilibrium is reached. If the concentration of the product is decreased, more reactants will react until equilibrium is also reached again. So for gaseous reactions at equilibrium, an increase in pressure causes the equilibrium position to shift towards the side with the smaller number of molecules as shown by the symbol equation to the right. So a decrease in pressure causes the equilibrium position to shift towards the side with the larger number of molecules, so it would go in reverse. So nitrogen gas and hydrogen gas are obtained from different sources. So what is the source of each of them? So nitrogen comes from the air, and hydrogen usually comes from the breakdown of natural gas. So if we're summarising what the chemical reaction is, chemical equilibrium is, it's got to be in a closed system, and the rate of forward and backward reactions are equal. So the Haber process, also called the Haber-Bosch process, is an artificial nitrogen fixation process and the main industrial procedure to produce ammonia. So we start off having to obtain hydrogen from the air, and hydrogen from gas and nitrogen from the air. Right, and they are pumped into a compressor through a series of pipes. The gases are pressurized to around 200 atmospheres. The pressurized gases are pumped into a tank containing beds of iron catalyst at about 450 degrees. In these conditions, some of the hydrogen and nitrogen will react to form ammonia. The unreacted hydrogen and nitrogen gases fed through the pipes to pass back through the iron catalyst again, so it won't be wasted and will get reused. This will improve the efficiency of the process. So if we're looking at explaining why iron is used, it's used as a catalyst, so it speeds up the reaction. If we're looking to describe how the ammonia is separated from the other gases, it's cooled down so it condenses or liquefies. So the pressure chosen for the Haber process is called a compromise. A high pressure increases the percentage yield of ammonia, but very high pressures are very expensive to maintain. The temperature chosen is also a compromise. A high temperature gives a fast reaction but decreases the percentage yield of ammonia, and both of these are shown in the graph to the right hand side. So we're looking to suggest and explain why the conditions used to produce ammonia in the Haber process are at 450 degrees and a pressure of 200 atmospheres. It's because the reaction is reversible. So the forward reaction is exothermic, so it's increased by a temperature but lowers the yield of ammonia. A lower temperature would decrease the rate of reaction. A high pressure would increase the yield, but a too high pressure would be very expensive to maintain. Thanks for watching.